Chapter 3 is going to go over polynomials, but we're going to start with a friendly and familiar polynomial, that is the parabola y equals ax squared plus bx plus c. So these have a nice almost U shape to them when you graph them, and there's going to be a lot of things that we're going to ask you to find when we graph these. We're going to ask you to find x and y-intercepts, vertex, domain and range, and a good problem to start out with is problem number 8. In part because it's already graphed for you. So we have y equals 3x squared plus 6x minus 1, like that. And they ask you to find a bunch of things. Now, the most important point in working with the graph of a parabola is to find the vertex. I mean, that's where the graph turns around, and it's a really important point here. So let's see, just by looking at the graph, if we can't estimate that point. Where's the vertex of this parabola? Good. -1 and -4. So there's your vertex. On an exam, that's 2 points. Let's keep getting a lot more here. Vertex is at -1 and -4. We'll see later how we can actually calculate that. There'll be a couple ways we can calculate that. Next, I want to find the Y-intercept. How can I do that in general? What do you have to do to find the Y-intercept of a graph? Yeah, the graph's going to cross the y-axis when x equals 0. So all we need to do to find the y-intercept, to find where this crosses, is just to set x equals 0. So let's do that. So the y-intercept, set x equals 0. So it's going to be y equals 3 times 0 squared plus 6 times 0 minus 1. I don't think I need my graphing calculator for this one. It's just a -1. So again, some easy points here for us. Now come the more challenging points. And that is, we got the y-intercept. What else do you think I'm going to want here? X-intercepts. So X-intercepts, how are we going to have to find those? Set y equals 0. So when I set y equals 0, I get 0 equals 3x squared plus 6x minus 1. And yeah, boy, now what are you going to do? Try factoring. I'm not sure it factors. So if it doesn't factor, then good. Your fallback on that is the quadratic formula. So let me remind you, did anyone have a teacher in high school or something like that that would sing the quadratic formula to their favorite fight song? Yeah? All right. No, I would not sing on even a bet or a dare. No, you don't want to hear that. No way. Let me tell you in Russian. Нет. So let's see here. A, B, and C for this particular problem. 3, 6, and -1. So -6 plus or minus the square root of 6 squared minus 4 times 3 times -1 over 2 times 3 is -6 plus or minus the square root of 36. And be careful here with the signs. Square root of 36 plus 12. Plus 12. So yeah, overall -6 plus or minus the square root of 48 over 6. Now I'm not sure that you really have to do it as part of this problem, but I'm sure that eventually there are going to be problems where you are going to need to do something like this, and that is square root of 48 can be simplified. That's the square root of 16 times the square root of 3. And of course, The choice for that, 16, is a nice perfect square. You got a list of your perfect squares on the left-hand side board. Just find the biggest one that divides 48, and that would be 16. Now, why did I split it up like that? What's the advantage here? Yeah, I could take the square root of 16 as 4. One thing you have to be careful about, you can't add these terms together. Why not? Yeah, this one's being multiplied by the square root of 3. They're not like terms. If the square root of 3 wasn't here, or if the 6 had a square root of 3, then I could combine them, but I can't. What I can do is I could factor out a 2 from the numerator. So negative 3 plus or minus 2 square roots of 3 over 6. And now, whew, man, get out the oxygen bottle, right? Now I can finally do some cancellation here. So 2 cancels into 6 3 times, and I'm left with negative 3 plus or minus 2 square roots of 3 over 3. As far as the decimal value, I probably could have gotten the same exact decimal value about 5 minutes ago way up here. But this is something that it doesn't hurt to review now. In fact, you don't need it for this part of the problem. But let's see if we can't get some decimal values there and see if they look right. In fact, let's look at the graph first here. What does it look like the decimal value should be here? What would you guess? Negative 2.06 maybe? Because that's a 3, so each one of these is going to be a quarter. So 0.18? Is that a guess? Yeah. Really? All right, that's good. Yeah, I was looking to see if his calculator was out. It wasn't. So, all right, so our numbers that we should get should make some sense, should be close to what we're seeing on the graph. Let's see that they do. So let's take out our graphing calculators, and I don't know, let me show you yet another trick about your graphing calculator. If you have an operating system that's up to date, your calculator can actually do fractions more or less like we write them. So where would you find that? Well, if you hit the alpha key and then the y equals key, it gives me this menu. And when I press enter, it gives me a straight up and down fraction. The advantage of that is you don't have to bother around with parentheses. So if you have that, great. If not, I'll go back and do this again in a second. So I want negative 3 plus 2 times the square root of 3. All divided by 3. So that's the first one. And we got something a little bit to the right of 0. A little bit to the right of the y-axis, which makes sense based on our graph, right? We expected something a little bit to the right of x equals 0. So let's see how we do on the other one. Now, if you don't have, this fancy capability with your calculator, that's okay. What you need then is parentheses around the numerator. So negative 3 minus 2 times the square root of 3. Exit the radical, right parenthesis, divided by 3. But you need parentheses around the whole thing. Now, one last little comment or one little trick here for you. After you've entered one of these, the smart thing to do is not have to type it all in twice. So, for instance, here, if I hit the second key, then the enter key. So second, then enter down here, it brings up my previous calculation. And all I have to do is go back and change the minus to a plus or plus to a minus, whichever one I started with. Once you have one, then you get the other one. So it's a little less painless. Have you guys seen a trick like that before? No? Is that a handy one? You like that one? Yeah, it's a good one. And you can keep, you can keep going back farther in your calculation history by continue to hit second enter if you want to go even further back. But So you said negative 2.18. You're pretty close. Negative 2.154. So, yeah. Oh, you already calculated that? That's great. All right, so we've gotten a couple of the major points here. There's some other stuff that the problem asks us. It asks us for the domain and the range. So let's look back at the graph here. What do you suppose the domain is? It's everything, right? This graph exists for all real numbers. So the domain is everything. So our domain is negative infinity to infinity, or better yet, all reals. All right, Jeff helped us out with the domain. Someone else pick up the range. What's the range going to be on this function? Thanks, Olivia. Negative 4 to infinity. So the range is your y values. So I think we nailed it for problem number 8. We've gotten everything that they asked for. The domain, the range. I guess there is one last thing that they do ask for. It says, find the minimum or maximum value of f. Well, the minimum value is this point right down here. So they're looking for negative 4 is your minimum value. But once you have the vertex, you've got the minimum or maximum value. Are we okay with problem number 8 there? Anything else you'd like me to say on that one? There's two ways to think of the domain here. One way is to look back at the original function and think about it and say, all right, well, is there anything that's going to cause this function to be undefined one way or another? So what would be that? That would be something if you had a square root. You want to make sure that the numbers underneath the square root are greater than or equal to 0. Well, we don't have to worry about that. The other problem that you could run into would be if you had a 0 in the denominator. Well, there's no denominators. So there's no points we have to throw out. So when you're looking at domain and range, or when you're looking at the domain, you start out with everything and throw out any points you need to throw out. There's no points we need to throw out. Polynomials are defined for all real numbers. There's no places where you're going to have a 0 denominator or a negative underneath the square root. So we're good on that one. The other way to do this is to kind of look at the graph and realize that this graph exists for all real numbers. That it's going to go out here further towards negative infinity and out towards positive infinity. So that, again, the graph exists for all real numbers. We're going to see something that doesn't exist for all real numbers. It would be something like y equals square root of 1 minus 2x. This was one from your most recent test. Okay, what's underneath the square root has to be positive. So that means x is less than or equal to 1/2. Yeah. Parabola would open up sideways if it was in y squared. So let me shut these off. If I had x equals y squared, then you're going to have a parabola that opens up sideways. All right. Thanks for the questions. Anything else before we move on? Okay. Let's look at problem number 16. It says a quadratic function is given. Express f in standard form. Find the vertex and x and y-intercepts. Sketch the graph. Find the domain and range. So pretty much like the last one, except they didn't give us the graph to start with, so we're going to have to do a little bit of work. And they also said something about standard form. So what's standard form? Well, standard form of a quadratic function is on page 246. So it's this. We're going to try and write our quadratic function not as ax squared plus bx plus c, but rather as a times x minus h squared plus k. And the advantage of that is you can just literally see the vertex when you're looking at the form of the equation. So you don't have to graph it at all. You'll just be able to look at it and tell what the graph or what the vertex will be. So problem 16. F of x is x squared minus 2x plus 2. And let's first put that in so-called standard form. So let me start by replacing f of x by y, just out of convenience. And then we're going to go through a process of completing the square. You might remember this from a previous class. So we have y equals x squared minus 2x plus 2. For convenience, I'm going to throw the 2 on the left-hand side for a second. That constant. And my goal here is to figure out a number that I could put here that makes the right-hand side what's called a perfect square trinomial. So that is, it'll factor as something times itself, or better yet, something squared. Now that process, to give you kind of a quick reminder, if you had x squared plus bx and you wanted to complete the square on that, the first step is to take 1/2 times b. Second step is to square the result from the first step. And that's going to be the number that you use to complete the square. So this is obviously an ultra-fast review. Hopefully it's something that you've seen before. What's that look like here? Well, I'll take 1/2 times negative 2. That's going to be negative 1. If I take negative 1 and square it, I get positive 1. And that's the number that I want to put right there. Let's put a positive 1 here. So if I put a positive 1 there, what else do I have to do? Thank you. You have to put a positive 1 on the left-hand side. So I put it on both sides. Now on the left-hand side, we get y minus 1. On the right-hand side, because of this excellent choice here of a 1, I can now write this as something squared. What do I square to get that right-hand side? X minus 1. Last but not least, let me take this 1 and put it back on the right-hand side. So I get y equals x minus 1 squared plus 1. And this is an alternative form of the graph that we started out with. But it has an advantage. Whereas up here at the start, f of x equals x squared minus 2x plus 2, if I asked you what that graph was like compared to a graph of y equals x squared, you'd be, I don't know, let me graph it. But here, you should be able to apply what you know about shifting graphs to figure out where that graph is now. How has this graph been shifted compared to y equals x squared? To the right one, up one. So the vertex, which was at 0, 0, has been shifted to the right one, up one. Where's the vertex now? 1, 1. And you can read that off, right? If you set x equal to 1, what would y equal? Well, 1 minus 1 is 0. Squared is still 0. Plus 1 is 1. So 1, 1 is your vertex. And it's really nice to have it like this because you can see what that vertex is now. So that was the first part of problem number 16, is to put it in that standard form. And I hope that you can see the advantage of that standard form. We'll practice another one like this. But are we okay with what we did here? And just as important, why we did that. It tells us what our vertex is. Yeah, this is just like our shifting stuff, right? The -1 shifts to the right by 1 horizontally. This is a vertical shift, and there'd be a +1, so there'd be an up 1. So the vertex, which was at 0, 0, was here, has now been shifted to the right 1 and up 1. So you've got a vertex here. So something like that. So 1, 1. Let's see if we can answer some other questions. So some of the other questions that are given to us are find the X and Y intercepts. Well, let's start with the Y-intercept. Y-intercept. For the Y-intercept, how do I find the Y-intercept? What do I got to do? Set X equal to 0, right? Now let me give you a choice. In fact, you've got a choice. Because you worked hard and because you have this equation in two forms, let's call it A and B. Which form do you think would be easier to find the Y-intercept from A or B? I'd say A. Why A? Yeah, just 2, right? Because you put in a 0 and that disappears. You put in a 0 and that disappears. So you're just left with a 2. Here, I'm ashamed to say we'd have to do some thinking. So let's avoid that, right? All right, so the Y-intercept is 2. Now, you get the same thing either way. If you put in a 0 here, -1 squared is 1, +1 is 2. So it works either way. I'm just trying to help you out. Work smarter, not harder. So Y-intercept, in fact, let's keep track of all our points here. X and Y. If we set X equals 0, we get Y equals 2. If we set X equal 1, we get Y equals 1. That's our vertex. There's another important advantage of putting this in standard form and just being able to visualize what the graph is. And that other advantage is finding the intercepts. Now, it's not really part of this problem, but it's something that I typically ask for when I ask for you to graph polynomials like this, when I ask you to graph parabolas in particular. Let's look at the graph. Can anyone tell me something about the X-intercepts? There are none, right? There just aren't. This graph does not cross the x-axis. So if you went looking for them, if you did, okay, let's set y equal to 0, I'll move the 1 to the other side, it becomes -1. Yeah. And then try and take the square root. What you'll find is that this graph crosses the x-axis only in your imagination, right? Because that's an imaginary number at this point. So there are no real or x-intercepts for this graph. Let's finish this up with domain and range. We found the vertex and y-intercepts. So let's look at the domain and range. Well, again, all I have is this really crude graph, but that's all I need. Why don't you take a second and think about domain and range, and I'll take a second and think about who I want to volunteer. Domain and range of the new one, or of this one. Y equals x minus 1 squared plus 1. Okay. Cooper, what's the domain, please? Good. All real numbers. Or you can write negative infinity to infinity. Nice. Kenny, how about the range, please? Perfect. 1 to infinity. In fact, silly me, I had this already graphed for you on your handout. What we can see there, again, the range from 1 to infinity. And your domain is, again, all real numbers. So domain is R, and the range is 1 to infinity. Are you comfortable with domain and range? I mean, especially the range is something that I think you're pretty much going to get from looking at the graph. Let's move on down to problem number 20. Now, before I get to problem 20, let me go back. Do you want another quick practice problem of completing the square here? All right. Probably not a bad idea. So, for instance, if I had y equals x squared minus, let's do a plus, thank you, 8x plus 5, let's see what we can do about completing the square in this case. So kind of like the last one, I'd move the 5 to the left-hand side and get y minus 5 equals x squared plus 8x. And there's 2 steps here. Do you remember what the first one is? Yeah, take half of the 8. So half of 8 is 4. 4 squared is 16. So 16 is what you have to add to both sides. On the left-hand side, this simplifies to y plus 11. On the right-hand side, that simplifies to what? X plus 4 squared. If you move the 11 back to the right-hand side, then you've got y equals x plus 4 squared minus 11. It's nice. I like that. You can read off the vertex from this. Paige, what's the vertex here, please? What are the coordinates? Close. You're still close. Minus 4, minus 11. All right, start with what makes the squared term 0. So it would be a minus 4. And if I made that term 0, if that disappeared, y would equal negative 11. So negative 4, negative 11. But it's nice to be able to read that straight off of your graph, or actually the equation. You don't even have to look at the graph. By the way, I'll just point this out. I'm not going to do it. But one way to double check yourself on this, that you did this right, would be to graph this equation and graph this equation. What should you notice when you graph both of these equations? It should be exactly the same. So if you take out your calculator and graph one parabola and graph the other, and they land on top of each other, it's a great double check of your work here. Let's move on to problem number 20. As typical in a lot of these problems, they're going to get harder as we go through. Problem number 20 is no different in that respect. So f of x is negative 3x squared plus 6x minus 2. So kind of follow along. There's a little bit of a trick here, and you're only going to see this trick once during my work in this section. And that is, before we start completing the square here, and I will move the 2 to the left-hand side, there's something I got to fix. In order to complete the square, the coefficient of x squared has to be 1. I can't have a negative 3 out in front. So I have to factor it out. So it's going to be y plus 2 equals negative 3 times x squared minus what? Minus 2x. Good. Now we're not taking out the greatest common factor here. All we're doing is we're taking out the coefficient. So, okay. Now I can complete the square on the inside term here. So it's going to be y plus 2 again equals negative 3 x squared minus 2x plus something. It's always going to be a plus when you complete the square here. What am I going to put in the parenthesis? Can you see that a 1 completes a square? Half of negative 2 is negative 1. Negative 1 squared is 1. So I'll put a 1 there. But I got to be really careful. If I put a negative 1 here, what am I going to put on the left-hand side to keep things in balance? All right, so negative 3 times 1 is negative 3. So to keep things in balance, I'm going to put a negative 3. Good job. But do you see where that negative 3 comes from? It comes from the product of this and the 1. So negative 3 times 1. That's where that comes from. Are you okay with that step? That's the tricky part here. The rest of it is pretty much the same. The left-hand side is y minus 1. The right-hand side is negative 3 times x minus 1 squared. Move the 1 back to the right-hand side. Y equals negative 3 times x minus 1 squared plus 1. Yes? This term right here, going from here to here. So this factors, if you're just looking at this, that would factor as x minus 1 times x minus 1. So we choose to write it as a squared. Okay? And when you choose this number carefully, it's always going to factor like this as a binomial times itself, making this a perfect square trinomial, meaning it's a square of a binomial. All right? So, yeah, you can always double check yourself like that. What's the vertex? Good. So let's keep track of things in a little t-table here. Vertex is 1 and 1. Ooh. Who can be the first to tell me the Y-intercept? 0, negative 2. Nice. Now remember, you've got two choices as to where you want to find the Y-intercept. You can do it down here, or you can do it up here. I do it up here because it's easy to put in a 0 and here and here and see that you get a negative 2. So 0 and negative 2. Last but not least, we want to find the X-intercepts. Now, this one you got more choices as to how you do it. If you use the first equation and set this equal to 0, I'd probably use the quadratic formula. There's nothing wrong with that. If we use this one, well, then I'm going to take a different approach. Let's use this one just to show you some variety here. So let's set y equals 0 here. And for my convenience in solving this, see, I want to get that squared term by itself. I'm going to move that squared term to the left-hand side rather than moving the 1 to the left-hand side. Can anyone tell me why I'm picking up that big, heavy term and moving it all the way over to the left-hand side? Yeah, so I don't have to deal with that negative there. Moving this to the left-hand side gets rid of that negative. So it's going to be 3 times x minus 1 squared equals 1. Let's divide both sides by 3. And that's looking a little bit more reasonable. X minus 1 squared equals 3. What do I do to keep solving for x? Square root. So I get x minus 1 equals plus or minus the square root of 1/3. I'm almost done, right? The only thing left to do is to add 1 to both sides. X equals 1 plus or minus the square root of 1/3. Now the book would probably rationalize this. They'll give you 1 plus or minus the square root of 3 over 3. But if all you're doing is graphing it, it's enough to have this. That's fine. Both of these are exact answers. It would help us out if we knew what those decimal values were in order to graph this a little bit better. So let's again take out our calculators to figure that out. So I've got y is 0 and 1 plus the square root of 1/3. Now leave yourself some space in your table because I want to put a decimal approximation there. And 1 minus the square root of 1/3. Let's do our decimal approximations. So 1 plus the square root of 1 divided by 3. Hit the second key and then the enter key. Go back and change that to a minus. So we've got both of those. Now when you're graphing these things, I'm not going to take out a microscope or a magnifying glass to look at things. All we need is a rough approximation. To the nearest tenth is fine. So this is about 1.6 and this is about 0.4. So both of those are good approximations, good enough. So we got a lot of information here. Are you okay with how we got this information? Cooper?
If there's a question on the exam, would you, for the X-Intercepts, if we had used the quadratic formula, could we plug in the calculator, or do you want us to show the work?
It depends if I ask for an exact answer or not. If I ask for an exact answer, then the calculator is going to give you decimal values. It's not going to give you, 1 plus or minus the square root of 3 over 3. So that's the exact answer that I'd be looking for. If I just say graph it and I don't ask for the exact values, then you can kind of get away with that. I guess the one thing that I'm concerned about is that I want to make sure that you actually know how to find those rather than make your calculator find them. So I'll be careful in the way I ask the questions, but I hope the answer helps you out. Kenny? Yeah. Oh, absolutely. Yeah. I'm much happier with an exact answer as opposed to approximation. Yeah. This part is just so that when we go graphing it and we've got a spot to graph it on our handout that we know where to put this. Because I could look at this and go, okay, yeah, that's the root, but where is that? I wouldn't know until you get the decimal approximation. Katie?
Back when it was -3 and then times x squared minus 2x, where did the 2x come?
We factored out the -3 from both of those. So when you divide -3 into this, you get a 1. Divide this by -3, you get a -2. All right? Let's graph this. Finish this one up. We've got a vertex at 1, 1. That's up here. We've got a y-intercept at 0, -2. Now already, if this is the vertex and I've got a y-intercept here, that's telling you that this faces down, right? It has to open down. What else about this problem could tell you that it opened down? Yeah, the negative in front of the 3 here. So last but not least, let's put in some decimal approximations. We have a root at approximately 1.6 and another one at 0.4. And that's what those decimal approximations are for here, so that you know about where to draw it. And I've given you something that's fine enough along the x-axis so you can approximate it without really having to break a sweat. So we got that part And finish it off this way. By the way, if you're really careful, if you want to be really careful, there's actually another point that you can kind of get for free. This is an axis of symmetry for your graph. So if I have a point over here, then I have a symmetric point over here. So it's not a big deal, but if you wanted to have a little bit more accurate of a graph, you can do that. Overall, our graph looks like this. Let's take a break here, and we'll come back and finish up this section.